compilation is often viewed as a direct one-to-one translation, where human-readable source code is simply swapped for machine code equivalents. In practice, the compiler performs a mathematical restructuring of that logic. It breaks down the source text into foundational blocks to satisfy the specific physical requirements of the target hardware. This process begins with abstract syntax parsing, moves through layers of intermediate optimization, and concludes by mapping the logic into defined memory boundaries. A direct translation of the original source text would result in an executable that consumes more memory and processor cycles than necessary. To avoid this, the compiler manages two distinct environments: the logical space, where code is structured and optimized, and the physical space, where that logic is assigned a hardware address. The backend pipeline handles the transition between these two spaces, ensuring that the high-level logic remains functional while meeting the machine's operational constraints. YAC, an LALR1 parser generator, creates the initial structure in the logical space. It takes a formal grammar and produces the C code required to analyze the program's syntax. A YAC file is organized into three specific sections. The top panel contains declarations, the middle section holds the translation rules for the grammar, and the bottom panel contains supporting C routines. The process relies on two functions: YILEX, which scans the input for discrete tokens, and YIParse, which executes the parsing logic based on the grammar rules. System priority is established through precedence rules. In a YAC specification, operators defined lower in the list are assigned higher priority during mathematical evaluation. Explicit precedence is required to resolve ambiguous grammars, where a single expression might otherwise result in multiple valid parse trees. Precision is necessary during this stage, as an error in a follow set will result in an incorrect SLR parsing table, preventing the compiler from correctly identifying the code structure. By defining these rules, YAC establishes the logical framework necessary for the subsequent stages of optimization. After parsing, the compiler generates an intermediate representation. While abstract syntax trees are common, they may contain redundant entries if the same computation appears multiple times in the source. This diagram shows A equals B plus C times B plus C plus D as a binary tree. The B plus C subexpression appears twice, causing duplicate calculations. A directed acyclic graph optimizes this by merging these common subexpressions into a single node. To build the DAG, the compiler creates leaf nodes for B, C, and D, then an addition node for the first B plus C. For the second B plus C term, it routes the multiplication node back to the existing addition node, creating a shared reference. The root addition node is then connected to this multiplication result and the D leaf, followed by an assignment node for the variable A. The presence of shared nodes in the graph confirms that the compiler has identified the redundancy and reduced the total number of operations required. From the graph structure, the compiler generates 3-address code, a linear format used for step-by-step evaluation. In the expression x equals A plus B times C, the compiler must track the intermediate results of each operation before arriving at the final value for x. There are two primary formats for this data. On the left, quadruples use 4 fields: operator, argument 1, argument 2, and the result. In the quadruples format, the compiler generates temporary variables, such as T1 and T2, to store every intermediate calculation, which increases memory usage. The table on the right shows the triples format, which uses only 3 fields by removing the explicit result column. Triples refer to previous results using pointer indices. Instead of creating a temporary variable, a subsequent operation simply points to the index of a previous line to retrieve its value. Using triples allows the compiler to represent the same logic using fewer fields, reducing the memory overhead of the intermediate code. During code generation, the compiler must handle goto instructions. This creates a problem when the target of a jump is a block of code that hasn't been processed yet. Consider the conditional statement: if A less than B or C less than D, x equals 1. The compiler resolves unknown jump targets in a single pass using a technique called Boolean backpatching. As the compiler scans the code, it generates the jump instructions but leaves the target addresses empty. These are placeholders for line numbers that are currently unknown. For the first condition, A less than B, the compiler generates a jump to the x equals 1 block for a true result and a jump to the next condition for a false result. It repeats this for C less than D, noting the true and false paths. Once processed, the compiler fills in the target addresses, like lines 104 and 106, completing the flow. Backpatching allows the compiler to generate efficient code in a single scan without needing to reread the source file to resolve jump targets. The final step in the pipeline is mapping this optimized logic into the machine's physical memory hierarchy. The code section stores machine instructions, while the static data section holds global variables and constants. Both sections have fixed sizes. The remaining memory is dynamic. The stack, which manages function calls, grows downward, while the heap, used for dynamic allocation, grows upward. Each function call generates an activation record, or stack frame, which is pushed onto the stack to manage the function's local state. This diagram shows the organization of a single frame. It includes space for parameters, the return value, and the saved machine status, which preserves register values for the caller. 2 pointers maintain the connection between frames. The control link points to the caller's record, and the access link allows the function to reach data in nested procedures. These activation records represent the final stage of the process, where the compiler's logical optimizations are translated into a concrete physical structure in memory. The compiler pipeline moves from the formal grammar rules of YAC to the elimination of redundant logic in DAGs and the memory compression of triples. It resolves control flow using backpatching and organizes the result into a structured memory stack. Maintaining precision throughout these stages is critical. An error in the graph construction or a misunderstanding of the stack frame can lead to increased memory usage or runtime failure. Through this series of transformations, the compiler converts high-level programming abstractions into a format that adheres to the physical constraints of the computer's hardware.